Hi everyone, I'm very happy to be telling you about parallel repetition for the GHZ theorem, a simplified proof. This is based on a joint work with Justin, Kunal, Ron, and Yuen. I'll start by giving you a quick preview of our results, and then I'll go on to describe the background for our results. So here is our main theorem. We give a new proof that the parallel repetition value of the Endfold GHZ game is at most inverse polynomial in N. So parallel repetition of the GHZ game reduces the value of the game polynomially quickly. This was first shown by Justin and Ron last year. We give a new proof of this theorem that we believe to be much more simpler and more. So this is our main result. I'll go on now to describe the background for our result. So the setting is this, multiplayer games. So what is a multiplayer game? You have a verifier and you have a few players. The verifier samples some questions from some distribution and sends different questions to the different players. The players don't communicate with each other. They look at the questions they receive, and based on that, they come up with an answer. And their goal is to answer in such a way that some predicate is satisfied with high probability. So more formally, a verifier samples an input X from some distribution mu and sends the ith part of the input to the ith player. The player I looks at xi and comes up with an answer yi. This yi depends only on xi. It does not depend on any of the xj where j is different from I. And we say that the game is won on input x and answers y if the predicate v of x comma y is 1. We say that the game is lost on input x and answers y if the predicate is not satisfied. So this is a multiplayer game, and the goal of the players is to maximize the probability that this predicate is satisfied. So the value of the game is the maximum probability of winning this game. This maximum is taken over player strategies. And by a strategy, we just mean a function that maps xi to yi. A function that tells each player what answer they must give on any particular question. Without loss of generality, we can assume that this function is deterministic, because if they had a randomized strategy, by linearity of expectation, you can fix the randomness so that the resulting deterministic strategy does at least as well as the randomized strategy. So for us, the strategy is just going to be a deterministic function from xi to yi for each player. The probability here is taken over inputs x drawn according to the distribution mu. So this is a multiplayer game.
So a game is defined just by the distribution and by the verifier function.
Yes. So, right. So the only thing you need to define this is the number of players, the distribution on the inputs, and the predicate. And just to emphasize here what is known, the parameter, the distribution mu is known to all the players. The predicate is also known to all the players. And you can assume that the player strategy is fixed. That is, the players agree on an optimal strategy and they're going to follow that strategy. So the only unknown here is the inputs to the players. So player I only knows xi and therefore knows yi. This player is not aware of the inputs to the other players. So this is the only unknown here. Okay, so now that we've defined multiplayer games, let's look at an example of a multiplayer game. Let's look at the GHZ game. So this is a 3-player game. The verifier samples a random input XYZ from this distribution, so the uniform distribution on these 4 points, 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. You can also think of these 4 points as the hyperplane over F2 cube defined by points x, y, z, such that x plus y plus z is 0. So 0 mod 2. So I'll often refer to this distribution, the uniform distribution on these 4 points, as the GHZ distribution. And the verifier sends x to Alice, y to Bob, and z to Charlie. Alice, Bob, and Charlie need to reply with bits A, B, and C, such that this predicate is satisfied. So x or y or z equals A plus B plus C. The addition is modulo 2. So this is the GHZ game. One strategy that the players can follow is to always return 1. In this case, you can see that the players lose only on input 0, 0, 0. So here is a strategy that wins with probability 3/4. In fact, you can show that this strategy is optimal. That is, every strategy can get a success probability of at most 3/4. So the value of the GHZ game is 3/4. So now let us move on to parallel repetition of a multiplayer game.
So just before, can you go back? Yeah, I guess for people who haven't seen it, this is a natural generalization of a game on 2 players, which is very famous from physics. I don't know if you'll talk about it.
No, I will not talk about, I will mention about the quantum aspects of GHZ, but not about the
So it's the foundations of quantum mechanics, the Einstein-Podolsky-Rosen challenge, EPR paradox, and the Bell inequalities refer to similar games with just 2 parties. And if you remove one party, the same function basically reveals the power between, I don't know, quantum provers and classical provers. Okay, that's a natural extension.
Yes. So this might actually be a good point to mention something I was going to mention later, which is that this game can be won with probability 1 if you have quantum strategies. So if the players are allowed to share entanglement, then there is a strategy that actually achieves value 1. And this is actually pretty robust in the sense that anything that gets value 1 must involve the players sharing a particular type of entanglement. And in fact, any strategy that gets value close to 1, the players must share a state that is close to this particular type of entanglement. So this is a game that's been studied a lot in quantum information theory. For our talk, we'll be focusing on the classical aspects of this problem. So now let me define what Endfold parallel repetition is. So in the Endfold parallel repetition of a game, the players are given n independent instances of the game, and their goal is to solve all the instances simultaneously. So here the verifier samples n independent times from this distribution mu and sends the ith part of each of the n instances to the ith player. The player I looks at all these instances and comes up with answers for all the n instances. So note here that, for example, the answer that player 1 gives on the first instance can depend on the inputs to all the instances. And the goal of the players is to satisfy all the predicates. So this is the Endfold parallel repetition of the game, and we are interested in value. So we denote this by g to the n, and we're interested in value of g to the n, which is the maximum probability of winning when the inputs are drawn from this mu to the n, which is the tensor product of mu n times. And the maximum is taken over strategies for the Endfold game. So by a strategy for the Endfold game, I mean a function which maps n inputs to n outputs for each player. So this is the value of the Endfold parallel repetition of G. And the big question here is, what is the asymptotic behavior of value of G to the n? How does value of G to the n behave as n goes to infinity? How does parallel repetition affect the value of the game? So this is a really natural question to ask. You have a game, you're trying to reduce the value by repeating it in parallel. And the question is, how fast does this value go to 0? It turns out that for 2-player games, this question has close connections with PCPs and hardness of approximation and hardness amplification and so on. It also has connections to other areas like quantum information, geometry of forms, and communication complexity. For games with 3 or more players, it was recently shown by Kunal and Ran that strong parallel repetition for certain types of multiplayer games implies non-uniform Turing machine lower bounds that were not known before. So this is one reason why we might want to study multiplayer parallel repetition. But more generally, there is this intuition in the field that the kind of bottlenecks you encounter while trying to prove multiplayer parallel repetition is very similar to the kind of bottlenecks you encounter while proving number on forehead lower bounds in communication complexity. So one might hope that proving new techniques to prove parallel repetition lower bounds has applications in other settings as well. So here are some motivations for studying the parallel repetition question. What do we know about the parallel repetition question? So one easy thing is that value of g to the n is at least value of g to the power n. This is because the players can take an optimal strategy for the original game and just play each of the n instances independently. Since each individual game is one with probability value of g, and the n instances are played independently, the probability of winning all the instances is value of g to the power n. So this is a lower bound on the value of g to the n. One might expect that the value of g to the n is at most value of g to the n. However, this is not true. And the difference here is that the questions are given in parallel. Imagine that these questions were given sequentially and that the game was played one after the other, that the questions were given one by one and the players had to answer one by one. In this case, really, there is nothing better they can do. However, when the questions are given in parallel, each player gets to see a bunch of questions in one go. As a result, he can correlate the answers across different instances because he can see all the questions. Therefore, the n games don't behave independently because of this correlation that is introduced by the players answering correlated answers. In fact, there exist games for which value of g to the n is much larger than value of g to the power n. So this correlation that the players introduce by their answers really complicates the situation. So what do we know about this question? For two-player games, the most important result here is the parallel repetition theorem. This is due to Raz, and it was later simplified by Holmgren. This shows that if the value of the initial game is at most 1, then...
Less than.
Oh, sorry, less than 1, not including 1, but strictly less than 1. Then the value of, this should be g to the n. The value of the n-fold parallel repetition of g is at most exponentially small in n. So parallel repetition decreases the value exponentially fast for two-player games.
Let me mention that there was an earlier result just showing that the value of g to the n goes to 0. This by itself is not trivial, and it follows from the Hertz-Joule theorem from the theory.
Can you give the simplest example in which you gain something from having all instances in parallel?
It probably takes a few minutes.
Yeah, so it's not
there is a simple game where you repeat it with two players, or you repeat it, let's say it has value half, and you repeat it twice, and it still has value half. Yeah, there are simple games, but probably, it will take afterwards.
Okay.
Right. So although you can't really say value of g to the n decreases as exponential in value of g, but it does decay exponentially. So this is almost the best thing that we can hope for.
Maybe one should say this was a huge result when one proved it, and it's used everywhere, and it's taken for granted in the whole PCP literature since then.
Right. So yeah, this is a very important and powerful result. So now we also know tighter bounds if based on the value of the initial game. So this is the situation for two-player games. For games with 3 or more players, the situation is less understood. So the best result we have is the one that Avi just mentioned, which is that if the value of g is strictly less than 1, then value of g to the n goes to 0. And this rate at which it goes to 0 is extremely small. So it's 1 over alpha n, where alpha n is the inverse Ackermann function. And this follows by an application of Hales-Joule theorem. This is the best result that we know for all games. For special kinds of games, you have better results. So for example, for expanding games, Dinur, Harsha, Venkat, and Yuen showed that if the value of the original game is less than 1, then the value goes to 0 exponentially fast.
Are you going to define expanding games?
Yes, well, not expanding games. So yeah, in the next slide, I'm going to present a simplification of the result. So let's see that. So I'm just going to present the result for connected games. And what is a connected game? It's basically a game where the graph on player inputs is connected. So what is this graph on player inputs? The vertices are all possible inputs to all players. So it's a k-tuple, all possible k-tuples of questions. And you connect two vertices x and x prime if they agree on all except one coordinate. So they agree on the questions to all players except one. We connect any two such inputs. And if this graph is connected, we say that the game is connected.
One question. If I do the Endfold parallel repetition on a 3-sat or 3XOR instance, is it still a 3-sat or 3XOR instance?
So, so what do you mean by this 3-sat instance?
Like, so do I get a newer instance of the same predicate just on a bigger variable set? Is there any such example where this happens for higher arity?
So,
how many players in your game? Can you say what the game you are asking about?
Yeah, so like 3-sat can be thought of as a game, right?
But
3 players.
3 players. Usually it's 2 players. It's closed versus variable.
No, yeah, so I don't want to do that. I want to think of
So
3-sat.
that's what she is asking you to say what the game you are talking about is.
Oh, I see. So you have 3 variable sets, X, Y, and Z, and then sort of all 3-sat clauses are on X1, Y2, Z3 or something. They're of that form. Okay, yeah, so a 3-partite 3-sat, I guess, is the right way to ask it.
But what is the predicate?
The predicate is 3-sat. You can think of it as a 3.
But then you don't test consistency in any way.
Sorry?
You don't test consistency in any way.
I think he's kind of saying that the verifier samples a random clause and gives the variables to the players. Is that what you mean? Yeah, so like if you just repeat it, like, so like the new 3-sat, you can kind of write as like a constraint satisfaction on like these sets of variables that are like the Endfold products, right?
Yeah. And
so that you can do, right?
And is the new predicate still 3-sat? That's kind of what I'm wondering. Okay, I guess I'll take it offline. Yeah. So.
Yeah, I guess it depends on the type of predicate, and maybe for some predicates this is possible. I'm not sure.
I mean, given that it is just 3 players, it is a 3-sat, right? Or from what?
Maybe on n variables now and stuff.
Yeah. So you'll also have like an and of I is equal to 1 to n of over the repetition.
Ah, nice. Yeah. Thank you.
It's an and of all the predicates. So maybe.
So.
Yeah. Thank
you. Okay. So right. So about this result. So this is saying that whenever this graph is connected, then you actually have exponential decay for the parallel repetition. And the result they prove is actually stronger. So they give a tighter bound in terms of the expansion of this graph G. So that's their result. But for now, I'm just going to look at this result. So this leads us to naturally ask, what about disconnected games? So in this work, they suggest the GHZ game as a game that we need to study next, because if you look at the graph of this game, which we will see in the next slide again, this graph is highly disconnected. So to go from any one tuple of inputs to the other tuple of inputs, you need to change 2 coordinates. So this is a disconnected game. There is no edge in this graph. And one can ask, can we show parallel repetition for this game? So Dinur, Harsha, Venkat, and Yuen suspect that progress on bounding the value of the parallel repetition of the GHZ game will lead to progress on the general question of parallel repetition for all multiplayer games. So let's recap the GHZ game. So here the verifier samples an input uniformly at random from these 4 points, the GHZ distribution here. And note that to go from any one input to another, you need to change at least 2 coordinates. So this is a highly disconnected game. And so this is the recap of the GHZ game. And the question is, what happens to the value of the GHZ game as you do parallel repetition n times?
Can you give any intuition why connectivity is relevant to analyzing the game?
Right. So the proof of this goes by lifting 2-player parallel repetition techniques and applying some extra things. So this connectivity property, so let me see. So ultimately,
the connectivity property implies that any 2-player subgame of this is also connected.
That is true. So ultimately, what you need to show is that certain distributions are close so that the players can jointly sample from these distributions. And every time you have an edge in this graph, that graph implies that the 2 distributions corresponding to the endpoints of these edges are close. And finally, you want to be able to say this for all possible inputs. So if your graph was connected through these edges, all these distributions will be the same. So you can do this correlated sampling that you do in two-player parallel repetition. So yeah, in particular, our proof of the GHZ game is different from doing a correlated sampling, and it's very different. Okay. So this is the GHZ game. What's going to be important for the rest of this talk is these 4 points. You can actually forget the predicate and the value of this game. For the rest of the talk, remember what this distribution of these 4 points is.
The even point.
Sorry?
The even point.
Yes, the even Hamming weight points. So now let me state our result again, and now we're ready to understand what all these terms mean. So we show that the value of g to the n is at most inverse polynomial in n. Here g is the GHZ game. This was first shown by Justin and Ron, and we give a new proof of this theorem that we believe is simpler and more direct.
Is there any non-trivial lower bound for that? What is the belief regarding what it should be?
Yeah, it could very much be exponential. So there are 2 bottlenecks in our proof where the polynomial bound comes in, and also there is a bottleneck in the previous proof. But it would be very surprising if the value is inverse polynomial and not inverse exponential.
But is there a...
We don't have an example of a strategy that does better.
So there is no strategy better than the trivial one?
Yes. So it could be that this.
So if you repeat it, you can get, like, say, better than 3 by 4 to the n.
Oh, right. So yeah, there is this quantum strategy which you can round. So you can get some c to the n, which is slightly better than 3/4 to the n by taking a quantum strategy and rounding it. So this rounding, there is some constant associated with this rounding this STP, and you get that constant to the power n.
But this is true also for many other games. It's,
Right.
There's a non-trivial strategy, but doesn't mean that it does not decay from it.
Right.
Okay, but it's
still exponential decay.
Is it a classical strategy or a quantum strategy?
It's a classical strategy.
It's the rounding up of one.
Yeah, like
Yes.
for the GHZ game itself. So if you only had this game on 2 players, like, you just kind of remove the 3rd player. Like, even in that, you can do better. So essentially, like, you can kind of show just using that in this also you can do better.
Right. So this is the best we're able to prove, but one can hope for an exponential bound. So 2 remarks on our result. The first is that our result holds for any game on the same distribution whose value is less than 1. It's not important that this predicate is the GHZ predicate. It could be any predicate whose value is less than 1. And secondly, the distribution also doesn't need to be exactly the GHZ distribution. Anything with the same support would also work. And our second remark is that it's a little different from the previous proofs of parallel repetition. In particular, it does not use information theory or correlated sampling. It uses mainly Fourier analysis and combinatorial ideas. So this is what I wanted to say about our result. In the rest of this talk, I want to focus on giving you an idea of the proof involved, because this is the most interesting, technically interesting, and the motivating aspect of our work. So I'm going to present a proof overview. So feel free to interrupt me with questions if at any point you have them. So I'll start by presenting a standard simplification to most parallel repetition proofs. So most of the parallel repetition proofs start at this point, and that point is the claim. So before that, let me introduce some notation. We call P as the input distribution to the Endfold parallel repetition of the GHZ game. So it's exactly the GHZ distribution tensored n times. In other words, it's this distribution on x, y, z, where each x, y, z is an n-bit vector such that x plus y plus z is 0. Let gamma be any distribution on inputs to the Endfold GHZ game. Let j be a coordinate. We say that a coordinate j is hard for a distribution gamma if the probability of winning in that coordinate is at most 0.99, where the inputs are sampled from this distribution gamma.
Maybe it's worth saying that this is natural because there's some inductive argument at hand saying that you keep reducing the the success probability of the provers because there, in whatever you solved already, there remains some other hard instance, maybe distributed similarly to.
What does it mean, winning the game in the jth coordinate?
So if you look at just the predicate for the jth game, just look at winning that predicate.
Winning the game is a conjunction of winning each one of the coordinates.
I was confused between coordinates. I saw them as the numbers of the players, sometimes the numbers of the instances.
Yes, so n is the number of instances and the players are always going to be 3 players. Yeah, so now that we have this definition, it suffices to prove this claim. So what is this claim saying? It's saying for any product event E across the players. So E1 is a subset of Alice's inputs, E2 is a subset of Bob's inputs, E3 is a subset of Charlie's inputs. All these are inputs for the Endfold game. And the assumption is that the measure of E under this distribution P is large, then at least one coordinate is hard for the distribution P conditioned on E. Once you have this claim, it would imply that the value of the Endfold GHZ game is at most n to the minus omega 1. So this claim actually is slightly stronger than what I stated. So if you're able to prove this statement for events of even smaller measure, then you'll get the corresponding value on the corresponding bound on the value of the Endfold parallel repetition of the GHZ game. So this is saying originally our goal was to show that solving all coordinates is hard. Now our goal is to show that solving some coordinate is hard, but for the distribution P conditioned on E, where E is a product event across the players of not too small measure. So I'm going to assume this, but let me try to give a short justification for why you might expect this. So imagine when you're trying to prove this kind of parallel repetition theorem, you're trying to understand what is the probability of winning all coordinates, and you can break it up as understanding the probability of winning the ith coordinate conditioned on winning the first I-1 coordinates. So you're going to want to bound terms of this form. The thing is that the event of winning the first I-1 coordinates is not a product event. It's a slightly complicated event that depends on all the players' questions and answers. So instead, the idea is to fix the questions and answers to the players in the first I-1 coordinates. Now it becomes a product event because once you fix the questions and answers, that decides whether you win or not in the first I-1 coordinates.
Right, but why? I'm still a bit confused. Why isn't everything symmetric? What is the reason that the jth coordinate is different than any other?
The strategies might be quite complicated. So the strategy could be that if you receive something in that coordinate, do something else in this coordinate. So once you condition it on what?
Gamma is not symmetric.
Oh, sorry, could you repeat the question?
I'm saying gamma is not symmetric.
Oh, yes, but gamma is non-symmetric because the strategies are non-symmetric.
Exactly.
Right? When you proceed inductively, P conditioned on E will not be symmetric.
But even originally, the strategies could have been non-symmetric.
Yeah. The strategies are non-symmetric. That's where the non-symmetry arises because P itself is symmetric, right?
Yeah, but I mean, it sounds like every strategy you can just, I don't know, shuffle the coordinates in the beginning. Yeah.
No,
I'm just trying
that
to understand.
That still doesn't make it symmetric, even if it shuffles all the coordinates. That gives you invariance under Sn, but it doesn't give that. It's a product strategy that you do each coordinate independently.
No, I know. I'm just trying to understand what does it mean to be like this definition of being hard for a specific coordinate. Why would any?
So you're going to apply an induction, and you're going to see. You're going to say, well, if I solved up to these many coordinates, what happens on the next?
Okay, so this is like a question of like the specific strategies. This is defined.
You're fighting with every event. Corresponds to some strategy which you don't know. You have to work against all of them. So that's the assumption. And what do you care if it's not the next coordinate that's found? That proves that some coordinate is found.
Yeah, I guess also the optimal strategies are very unstructured. Like you cannot say that they must be of a certain form that all these behave symmetrically. So it's quite hard to argue about things like that, which is why we need to argue for general events that come out of these strategies that such a thing holds. So, okay, so I hope I've given some idea of how this claim might come. Now I'm going to focus on proving this claim for the GHZ distribution. So here is the high-level overview. We want to show that for any product event across the players of sufficient measure, at least one coordinate is hard for P conditioned on E. So the first step is going to be to identify a simple kind of distribution for which the hard coordinates are easy to pinpoint. So these are going to be called bow-tie distributions. We then approximate every large, we approximate P conditioned on E for every large product event by a convex combination of these simple distributions. Finally, we'll show that for most of the simple distributions that appear in this convex combination, actually many coordinates are hard. So it will follow that a typical coordinate is hard for P conditioned on E. So this is the high-level proof overview. I'm going to focus on parts 1 and 2 mainly in this talk. So let's see step 1. So to describe our proof, the best language is to use graphs. So I'm going to rephrase our problem in using graphs. So this graph is different from the input graph I described before. This is a graph on inputs to the Endfold game. More precisely on the left, you have the set of all possible Alice's inputs. This is a set of size 2 to the n. Similarly, on the right, you have Bob's inputs. And you connect every possible input between Alice and Bob. Observe that the edges of this complete bipartite graph are in one-to-one correspondence with inputs to the Endfold GHZ game. So given a vertex x and y on x of Alice's input and y in Bob's input, if you look at the edge x, y, it corresponds to the input x, y, x plus y. Conversely, given any input to the Endfold GHZ game, it must look like x, y, x plus y. And that corresponds to the edge x, y. So it's useful to keep this picture in mind for the rest of the talk. The edges of this graph represent inputs to the Endfold GHZ game. We're also going to label the edges of this graph by the sum of the endpoints. So under this labeling, each input to Charlie defines a perfect matching in this graph. For different matchings, you get, for different inputs to Charlie, you get different perfect matchings. And when you combine two different matchings, you get a bow tie. So a bow tie is basically a 2x2 complete bipartite graph where two of the edges come from one matching and two of the edges come from the other matching. So more formally, we say that these four edges, x0, y0, x0, y1, x1, y0, and x1, y1, we say that these four edges form a bow tie if x0 plus y0 equals x1 plus y1. So this is saying that these edges come from this particular matching. And this is equivalent to x0 plus y1 equals x1 plus y0. So to go from one equation to the other, you can just add y0 and y1 on both sides. So this is the formal definition, but just keep in mind this picture of two blue edges and two green edges that go like this. So as I mentioned, you can think of a bow tie as four edges. You can also think of them as four inputs to the Endfold GHZ game. And this correspondence is exactly as before. So x0, y0 corresponds to x0, y0, z0, where z0 is x0 plus y0. So when I say bow tie, sometimes I mean collection of four edges. Sometimes I mean a collection of four inputs. And finally, the bow tie distribution refers to the uniform distribution on the four elements of the bow tie. So it could be the uniform distribution on these four edges or uniform distribution on these four inputs to the GHZ game. So this is already starting to look like the GHZ distribution. In what sense? In the following sense. So imagine that the verifier samples x, y, z uniformly at random from these 4 points, sends x to Alice, y to Bob, and z to Charlie. So now Alice gets either X0 or Y1, Bob gets either Y0 or Y1, Charlie gets either Z0 or Z1, provided X, Y, Z are of this form. So you can make this more formal. So let us look at a bow tie such that X0 and X1 differ in the ith coordinate. In this case, the ith coordinate of the bow tie distribution looks exactly like the GHZ distribution. So in other words, whenever this X0 and X1 differ on the ith coordinate, the GHZ game can be embedded into the ith coordinate of the bow tie distribution. So if you write down the bow tie distribution, which is the uniform distribution on these 4 points, and you look at the ith coordinate, so each of these are n length vectors, and if you look at the ith coordinate, it's going to look exactly like this. So this is the claim. And the proof of this is pretty simple. So let's just look at it. So this assumption implies that X0i and X1i must together be 0 and 1. You can assume without loss of generality that X0i is 0 because you can just interchange the role of X0 and X1. Similarly, you can interchange the role of Y0 and Y1 to ensure this property. And using this information, you can compute what Z0i and Z1i must be. So using all this information, you can fill this table, and this is exactly what it would look like. So this leads us to define what it means for a bow tie to differ in the ith coordinate. We say that a bow tie differs in the ith coordinate if X0i is different from X1i. We could have made this definition for Y0 and Y1, but it's just equivalent. So what we have shown is that whenever a bow tie differs in the ith coordinate, then the ith coordinate of the bow tie distribution looks exactly like the GHZ distribution. So you can embed the GHZ query distribution into the ith coordinate of the bow tie distribution. In particular, the ith coordinate is hard for the bow tie distribution. So this completes step 1. We described these class of distributions that we call bow tie distributions. And we said whenever the bow tie differs in the ith coordinate, then the ith coordinate is hard. So we can easily pinpoint the hard coordinates of this distribution. So now I'll move on to the second step.
Just to make sure that I understand, if they don't differ, I guess the problem is trivial in that coordinate, right?
Right. It will be that X0 and X1 are same, Y0 and Y1 are same, and Z0, Z1 are same. So it will be that all of them get 0. Yeah.
So you have hardened coordinates and completely trivial coordinates.
Exactly, yeah. So some coordinates, everything is identical. Some coordinates, even one of them is different, then all of them will be different, and this will be the case.
Of course, the players will know which coordinate.
Yeah. Mm-hmm.
Okay. So now we'll move on to the second step. We're going to show that.
You describe really one distribution, or you think of the family, or you really describe where you pick a random bow tie, and that's.
Yes, all possible bow ties. So they could be
so
any
it's
subset.
separated to all bow ties.
Yes. So simple distributions are all possible bow ties, all possible bow tie distributions. Okay. So, right. So let's move on to the second part, which is to approximate P conditioned on E by bow tie distribution, the convex combination of bow tie distributions. So this is going to be the difficult step, and let's see how to do this. So this is what we want to show. For any event of large measure, we want to approximate P conditioned on E by a convex combination of bow tie distributions. Let's look at this picture using the graph language that I described before. So this event E defines a subset of inputs, and let's look at all the edges that correspond to those inputs. So E defines a subset of inputs to the Endfold GHZ game, and each such input defines an edge in this graph. So let G be the graph that consists of all edges whose corresponding inputs are in E. So event E describes a subset of edges, and the distribution P conditioned on E under this.
It's an induced subgraph, right? E1 is just an event on questions to the first player. So it may remove some vertices from the left side. So what you see is there's still a complete bipartite graph, but on subsets of the vertices to Alice.
Does that work well?
I don't think so.
No, so what? Yeah, so I'm missing something.
So E3 talks about
E3 might be a problem, right? Because E3 gives what X and Y.
Yeah, good, very good. Yeah, it may rule edges. Yeah, very good. Thanks.
But it is going to be regular, I think.
Yeah, it is not, it's a special kind of graph. It's not just arbitrary subset of edges, but it's not induced either.
Good.
But we look at what it is. Okay. And this distribution P conditioned on E is exactly the uniform distribution over edges in this graph. Furthermore, because your event has significant measure, this graph has many edges. So if your measure of the event was at least inverse polynomial, then this graph G has at least inverse polynomial fraction of all possible edges. And so to rephrase our problem in this graph language, what we want to show is that there is some distribution on bow ties. So here, for example, you have a blue bow tie, a purple bow tie, and a pink bow tie. If you sample a random bow tie from this distribution and a random edge from the bow tie, then what you get is close to the uniform distribution over all possible edges. So this is the kind of statement that we want to show.
Maybe before this sort of a trivial observation, clearly there are lots of bow ties in this graph. The density is so high that there are many bow ties.
Actually, yeah, we will look at it. So it's not clear that is the case. You need the density to be extremely high. Something close to like...
Maybe I'm missing something. I mean, in a graph, this graph is potentially it's 2 to the n side, right?
Right.
In any graph with, let's say, k vertices, if you have k to the 3/2 edges, you have a 4 cycle.
But these are induced matchings. Like these two matchings must come from the same.
So, right, very good. So yes. The bow ties should agree on the match. Good.
Yes, that's why we call them bow ties and not K2-2s.
Yes, okay, very good.
Yes, so let's see actually if you can just solve this combinatorially, which we will look into. So first, let me introduce a simplification. It turns out that you don't really need to find bow ties because of this product structure that we haven't fully exploited. So I claim that instead of finding bow ties, it suffices to find these Z-shaped objects. So what are these? You have 2 blue edges and 1 green edge in between. Whenever such an object is present, it implies that this edge must also be present and it must be green. The proof of this boils down to the fact that these edges come from a product event. It's really simple to describe, and here is the description of the proof. So the takeaway here is that because these edges come from this product event, it suffices to find these objects instead of bow ties. So what are these objects? These are cross edges in matchings. So now the question is, how do we find these objects and how do we cover the edges using these objects? So it turns out that there is something more going on than just density type arguments. So this question that we're trying to study kind of reduces to this combinatorial problem. This is a well-studied problem, the Rouja-Semeridi problem. This asks, what is the maximum number of edges in an n by n bipartite graph whose edges can be partitioned into n induced matchings? So what is the connection here? So let's call this number RSN. Suppose the number of edges in our graph G is less than RSN, then it could be the case that each of these MZs for various values of Z, it could be that each of them are induced matchings, in which case you will not be able to find a cross edge. So this is saying that if you want to understand this question, you need very good bounds on the Rouja-Semeridi number, but the best bounds on this quantity are pretty weak. So the best known bound is n squared divided by 2 to the omega log star n. N is the total number of vertices. N is the number of vertices on each side. And if anything, this would only imply that the value of g to the n is at most 2 to the minus omega log star n. So this is going to 0, but extremely slowly. So the reason I introduced this connection is to say that we are using something more than just density of edges. We're also going to use the product structure even more strongly. But here is the main assumption that we will be using, which is the assumption that the Fourier coefficients of the events E1, E2, and E3 are small. So here is our main lemma. Assume that the Fourier coefficients of E1, E2, E3 are at most delta in absolute value. Then the uniform distribution over edges can be approximated by a uniformly random edge in a uniformly random bow tie. So sample a random bow tie in the graph and sample a random edge in the bow tie. This distribution is going to be close to the uniform distribution over all possible edges in G. So this is the main lemma. So let me spend a little bit of time describing the proof of this lemma.
So first, the statement. You didn't really argue, so given there was a similar connection, it's not even clear that there is a bow tie.
Right.
If the density of edges is polynomially small as opposed to
yes,
this tiny fraction. Now you want to prove more, but I mean, we will see, let's say, if all Fourier coefficients are small, that there are many bow ties, for example.
Yes, exactly.
Okay.
So we will see that there are many bow ties and a typical edge does not occur in too many bow ties. So it's uniform. So actually, this is the next slide. We will see a proof and let's see. Okay, so the main idea behind the proof is to look at this distribution obtained by taking a random bow tie and a random edge. If you write this down as a probability vector, the probability that a particular edge is sampled is proportional to the number of bow ties that contain that edge. So this is exactly the distribution that we want to show is close to the uniform distribution. We're going to show that the L2 norm of this distribution is small. This would, by Cauchy-Schwarz, imply that this distribution V is close to the uniform distribution over edges. So how do we show that the L2 norm of this is small? We're going to show that the L2 norm of the numerator is small and this quantity is large. So in particular, we'll show that the number of bow ties is large. So here are going to be the two main things that we prove. So the first inequality is saying that the denominator is large, and the second is saying that the L2 norm of the numerator is small. So what is this first equation saying? Intuitively, it's saying that there are many bow ties in this graph. In particular, if you collect all the bow ties, they're kind of going to cover most of the edges. The second equation here is saying that a typical edge does not occur in too many bow ties. So the sum of squares of number of bow ties containing an edge is pretty small. So this would imply that the cover is kind of a uniform cover of the edges. So quantitatively, these are the bounds we get. We show that the total number of bow ties is at least 2 to the 3n times measure of E square. If G was a complete graph, you would get exactly 2 to the 3n bow ties. So this is the total number of bow ties ever possible. And this first equation is saying that you're off by a factor of measure of E square. For the second equation, we show that the sum of squares of number of bow ties containing NH is at most 2 to the 4n times PEQ. So 2 to the 4n is what you would get if your graph was the complete bipartite graph. And this is saying that you're off by a factor of PEQ. So these are our two main inequalities.
So far, if the probability of E would be even exponentially small, you would be fine. This is not where polynomiality helps you yet.
So the polynomiality comes from this delta. So how small can you make the Fourier coefficients? You can make them only polynomially small.
Okay.
So all of these terms had better be polynomially small, that is comparable to delta. So indeed, it does come up here. So, okay, so I'm not going to prove these inequalities, but instead I'm going to show you the heart of the analysis, which is Fourier analytic lemmas. And I'm going to hint at why these kind of lemmas might be useful to prove statements like this. So let's see the Fourier analysis that goes behind this. Here is the main lemma. So let A, B, C be subsets of F2 to the N. suppose the non-zero Fourier coefficients of C are all small, then the measure of A times B times C under the GHZ distribution is close to the measure of A times B times C under the uniform distribution. So this is saying that provided the Fourier coefficients of the set C are small, then you can approximate the measure of this product set ABC under the GHZ distribution by its measure under the uniform distribution. So this is a really powerful result. It's allowing us to replace expectations over this highly correlated GHZ distribution by expectations over this uniform distribution, which is highly uncorrelated.
This is the exact same intuition that goes into the three-term arithmetic progression analysis and the Harsha result of the
Exactly.
So predicate.
Right. So we are also going to like condition on large Fourier coefficients. This does not happen too much. And when the Fourier coefficients are small, some pseudo-random property holds. So yes, this is very similar to that. So this is powerful because it implies, for instance, you can estimate the measure of product events under the GHZ distribution. So assuming that the Fourier coefficients of E3 are small, it implies that the measure of E under this GHZ distribution is close to the product of measures of E1, E2, and E3. So this statement allows us to replace the uniform distribution, replace the GHZ distribution by the uniform distribution. So in some sense, it allows us to treat these correlated objects that define graphs by random graphs, so to speak. The proof of this is really simple. It's basically this slide. We make use of two properties. The first is the convolution property. This says that the expectation of this, this quantity under the GHZ distribution is exactly the sum of product of Fourier coefficients. This is a really simple property that follows from basic Fourier analysis. We will then use the assumption that the Fourier coefficients of C are small, and we use Cauchy-Schwarz. So these two things imply the lemma that we're looking for. So let me give you an example of how to use this lemma. So let's, for instance, try to count the number of edges in G. Finally, we want to count the number of bow ties and the number of bow ties containing an edge and so on. But let's just look at this toy example of counting the number of edges in G. So how do you count the number of edges in this graph? So for every input in your event, you have an edge in this graph. So the expression for the number of edges is exactly 2 to the 2n times the expectation of E1x, E2y, E3z under the GHZ distribution. So each of this gives you an element in your event, and that gives you an edge. Now this lemma allows us to replace this expectation by an expectation over uniformly random points. And this implies that the number of edges is exactly 2 to the 2n times measure of E1, measure of E2, measure of E3. So this kind of allows us to treat the graph as though it was random in some sense. And using this so we use this lemma as well as a higher dimensional version of it. So we use a variance version of the statement as well to prove the two inequalities that I mentioned before. So
you still didn't justify the assumption that delta is small.
Yes. So now the question on why can we assume that the Fourier coefficients are small? This is an argument that has appeared before, but so what we're going to show is this. So every time you have a large Fourier coefficient, it turns out that you can break up the event based on the Fourier coefficient, and you will not do this too many times. So whenever you have a Fourier coefficient whose modulus is at least delta, it means that there is some hyperplane over f2 to the n, such that the correlation of A with that hyperplane is larger than delta. So what we're going to do is to break up that event A based on the value of this linear equation. And we're going to keep doing this until all the correlations with all hyperplanes are small. And intuitively, every time you do this, it means that A has high correlation with some hyperplane. But because A is an event of large measure, this cannot happen too many times because it cannot have high correlation with too many hyperplanes, so to speak. Each time you do this step, you reveal some information about A. So this step does not happen too many times.
Although a word connected to this is the density increment argument. This occurs from the proof of Ross on three-term arithmetic progressions.
Right.
And this is very similar to Meshulam's case in the hypercube, where he proves three-term arithmetic progressions in the hypercube. There it's exactly hyperplane.
Right. So this is the justification for why we can reduce Fourier coefficients. So this completes step 2. What did we do? We took this product event E. We broke it up into components where the Fourier coefficients were small. And whenever these Fourier coefficients were small, we were able to approximate P conditioned on E by a convex combination of bow tie distributions. So finally, I'm going to show you that most of these bow ties differ on a large number of coordinates, but this is going to follow almost immediately from the fact that there are so many bow ties in this graph. So you can just look at this picture for now. So we have all possible bow ties that could ever exist, and we have bow ties in G. We showed that these occupy a polynomially large fraction of all possible bow ties. If you look at the bad bow ties, that is bow ties that differ in less than 10% of the coordinates, they're going to be an exponentially small fraction of all possible bow ties. And the reason is that when you sample a random x0, x1, y0, this is going to define a random bow tie. It's very unlikely that x0 and x1 differ in less than 10% of the coordinates. You expect them to differ on 50%. So the probability that they differ on less than 10% of the coordinates is exponentially small. So these bad bow ties are an exponentially small fraction of the universe, while the bow ties in G are a polynomially large fraction of the universe. So therefore, the bad bow ties are an exponentially small fraction of the bow ties in G. So this completes step 3. So just to recap the proof, in the first step, we introduced this concept of bow tie distributions. This is new to our work. These are simple distributions where the hard coordinates are easy to pinpoint. Second, we took this event E and we approximated P conditioned on E by a convex combination of bow tie distributions. For this, we first reduced the Fourier coefficients, and then under the assumption that the Fourier coefficients are small, we showed this desired approximation. And finally, we showed that most of the bow ties appearing in this convex combination are hard on a significant fraction of the coordinates. So this completes the proof overview. So to summarize this result, we show that the value of the Endfold parallel repetition of the GHZ game is at most inverse polynomial in N. And we present a new proof of this theorem that we believe to be simpler and more direct. So this brings me to the end of the talk. So any questions?
Thank you.
Questions? Could you look at the density increment slides for a second?
Which slide?
Density increment.
Oh, okay.
So is this for all 3 events, or do you do only for E3?
So this is a bit technical. So we need to do this for each of these separately and somehow combine them.
Right.
So there is some more detail involved. But we do it for each of the E1, E2, E3 separately, and then we combine them.
Okay.
Yeah. So here also you incur a polynomial loss, but that seems a bit more technical than.
Okay. No, let's just say, because later on there was a E1, E2, E3 prime, and I was like, okay. So
yes, all of them
it's done for each of them. Okay.
So what is the highest lower bound known for any repetition of a game? Is there anything super exponential for some game, or is it just what do people think about that?
I think we don't know anything better than exponential. We don't have any counterexample of.
So it could be that for any game there should be an exponential upper bound.
So you uncovered something beyond connectivity, this regular structure of the support, right? Like itself a hyperplane or a 3-term progression in this case. I'm sure it extends to K players in the same way. And then there are more structures that are known to be forbidden or exist in dense subsets by similar arguments. So I wonder, you feel that there is maybe some characterization of when, even if you want just polynomial decay, class of connected games is known, and this type of games is known, and where is the limit of this kind of approach, maybe?
Yeah, that's an interesting question. So as of now, the techniques seem very ad hoc and different. So the technique for connected games is very different from the technique for GHZ games. I would think that something like this might extend to the case when you have this pseudo-random property. Instead of the GHZ distribution, you have maybe some affine structure that we use in addition, but also this kind of pseudo-random property. So this technique might be a candidate in such situations. In general, it's not clear as to, so one candidate to try would be affine games and games which have this pseudo-random property for this particular technique. In general, I think the situation is less understood. The techniques for different games seem very ad hoc. It's not clear if there's a general paradigm into which all of them fall. Does that answer your question?
Yeah, well, I mean, it seems like a good things to explore there too.
Right.
More questions? Great, thanks a lot, Thomas.